Hi everyone, welcome to the Geekle conference. And we are starting the Node.js conference globally. A lot of people are here. Some of you might not hear the sound. Please adjust your sound control in your browser. It's individually for everyone. So now we are excited to announce our first speaker here for the junior track, and this is Colin Ihrig from a program committee member. Colin Ihrig is a member of the Node.js Technical Steering Committee, a libuv collaborator, Happy.js core team member, and the primary author of the WASI implementation used by Node.js. We are happy to see how many people are actually joining this conference, and we're also very thankful to the committee members for their attitude to the work and everything that they have done to us. Hi, Colin. How are you doing? Yeah, I can hear and see you now.
Good. Thank you for having me.
That's great. Tell us a few words about yourself before you're starting the conference, and then go to the topic.
I'm sorry, what was that?
Tell us a few words about yourself, like present yourself a little bit. People that are looking for you.
So I am a software engineer at Joyent. I've been working on the Node.js project since I think like 2014 or 2015.
Quite impressive.
Thank you. And I'm just excited to be here today and presenting the work on WASI that's been going on for the past few months.
That's great. And what's your topic about?
So it's the WebAssembly system interface in Node.js. WASI is how it's often referred to. It's a new kind of experimental technology for working with WebAssembly and giving it access to the underlying system. And then this talk explains what it is and how it kind of ties into Node.js.
That's perfect. Colin, we are enabling you now to your main streamline, so you can go ahead. I guess I can add your share screen, and I'm disabling myself. So good luck to you.
Thank you. So thanks everybody for tuning in and attending my conference remotely. Good morning or whatever time of the day it might be for you. The title of my talk is the WebAssembly System Interface in Node.js. So I wanted to start off and kind of ease into what WebAssembly is in general. So this is the first bit of text you see whenever you go to webassembly.org. So WebAssembly, abbreviated WASM, is a binary instruction format for a stack-based virtual machine. WASM is designed as a portable target for compilation of high-level languages like C, C++, and Rust, enabling deployment on the web for client and server applications. So that's supposed to tell you what WASM is in two sentences, but they're pretty loaded sentences. So let's kind of go through them bit by bit. So obviously, the name of the technology is WebAssembly, but it's kind of a mouthful. So people, programmers, as they often do, have abbreviated it down to WASM. It's a binary instruction format. So if you think about assembly on, regular assembler on a computer, it's a very low-level way that sits just above machine code of telling a computer what to do. So this is kind of the web's version of that. And so you're not really intended to write WebAssembly by hand. It's supposed to be a compilation target. And they kind of hint at that in the second sentence where they mention C, C++, Rust. That's a handful of the languages that can compile down to WebAssembly. But in general, you'll be writing WebAssembly in some other language and then compiling down to it. So I'm not going to cover Rust much in this talk. I'm going to work more through the C, C++ workflow because that's what I'm a little more familiar with. But I just wanted to mention that Rust actually has really good support for WebAssembly. So if you're interested in WebAssembly or Rust, I highly recommend that you look into that. So back to the first sentence, after we have binary instruction format, we have a stack-based virtual machine. So the virtual machine part refers to the fact that you're not dealing with a physical machine. As far as I know, there's no physical hardware out there that runs the WebAssembly instruction set. And then stack-based refers to the conceptual way that WebAssembly works. So there is an execution stack. For example, when you call a function, you will actually push the function's arguments onto the stack, and then you will perform some operation on the stack. So, for example, an addition will pop the first two values off of the stack, add them together, and then push the value back onto the stack. So that is kind of at a very high level what WebAssembly is. So next, I wanted to talk a little bit about why you might want to use a WebAssembly and a couple more details about it. So the biggest reason that I think people would choose WebAssembly is that on the web, it gives you the opportunity for pretty decent performance improvements over JavaScript. The reason for that is that it's a much simpler format and it's binary. So as it's loaded into either the browser or Node.js or wherever you're running it, there's significantly less parsing that's involved and much less complicated syntax. So the less that the JavaScript engine has to do, or whatever engine has to do to run your code, generally the faster it's going to be. Also, compared to JavaScript, WebAssembly does not have a garbage collector, which leads to more predictable performance. So one of the main issues with JavaScript and other garbage collected languages is that your application can be running along just fine. All of a sudden, the garbage collector needs to run, and you'll notice a hiccup as your application kind of pauses so the garbage can be collected. WebAssembly is also sandboxed for security purposes. So this is one of the core tenets of WebAssembly is security and sandboxing and isolation. That means that you can pretty predictably assume that if you're downloading and running WebAssembly code, it's not going to be able to delete files from your hard drive and things of that nature. Going along with the sandboxing principle, there's not really any way to get into or out of the sandbox without explicitly giving import and export. So these are kind of functions that you can pass in that will give the WebAssembly sandbox something that they can call that can then operate on something outside of the sandbox. And WebAssembly also has pretty limited data types at the moment. So i32 and i64 are 32-bit and 64-bit integers. Similarly, there are floating point 32-bit and 64-bit numbers. But just based on these primitives, you can also create a number of other data types. For example, if you have a string, you'll actually have a WebAssembly memory that you can read data from or write data to. And by giving it a 32-bit integer, you can actually point to an address in that linear memory where a string would start, and then you would give it a second 32-bit integer to kind of denote the string length. And so that's how you can kind of build up more sophisticated data types based on integers alone. So as I said before, WebAssembly is not something that you're going to want to write by hand. So to kind of deal with that, they've created something called the WebAssembly text format. It's usually shortened to WUT. And this is it's a program representation. It's the same as the actual WASM code, but it's written using S expressions, which are a textual way to represent trees. So you can think of it as kind of writing your program's abstract syntax tree in text format. And I have a little example down here below. This format can represent everything that WebAssembly needs to represent, so modules, functions, imports, exports, etc. So we actually have a really simple module here that exports a single method. That method's name is add2, which you can see on the second line. This function takes 2 input parameters and returns a single result. Both of the parameters the 32-bit integers, so named num1 and num2, and then the result is also a 32-bit integer. So then on the third and fourth lines, you'll see these get local calls. This is just the WebAssembly way of taking the inputs to the function and pushing them onto the execution stack. So get local num1 will actually take the first input parameter and push it onto the stack. Similarly, get local num2 will take the second input and push it onto the stack. And then finally, we have this i32.add. This is telling the WebAssembly interpreter to take the top two values on the stack, which we now know are our inputs, add them together, and then push the result back onto the stack. And you'll notice that there's no return value specifically denoted here. Again, that goes back to WebAssembly being a stack-based machine. So it just kind of implies that whatever the top value on the stack is the return value. So the result of our i32.add was pushed onto the stack and is implicitly returned as our function's return value. So even with the WebAssembly text format, we're still dealing with fairly low-level stuff. You're probably not going to want to write anything too significant in that by hand. And when you're dealing with all these low-level formats and binary formats, it's nice to have tools that you can use to kind of automate a lot of things for you. That's where the WebAssembly binary toolkit comes into the picture. So it's abbreviated as WABT, but it's pronounced WABT. It's a popular WebAssembly toolchain that allows you to do a lot of neat things like converting between WUT and WASM and even C. So the generated C is not necessarily pretty, but it'll get the job done. And then there are some other tools in there that can do things like dump out symbols from a WebAssembly file. There's a whole interpreter in there, so you can actually execute WebAssembly code. It'll interpret all the .wasm files and then generate the output for you. And then I've included the link down below to where you can get WABT. So if you want to do any experimentation with WebAssembly, I highly recommend that you install WABT on your machine. So these are just a few example commands. At the very top of the slide is the exact same function that we had shown before, the WUT example. These are just some commands that you can run once you have WABT installed. So WUT to WASM is going to take this WUT file that you specify. So for the purposes of this slide, we're calling it example.WUT. And then it'll generate example.wasm for you. So now that you have a WASM file, that's actually something that you can load into Node or into a browser and actually run some of the WebAssembly APIs with it. And then I've also included examples of WASM to C. So that takes your .wasm file that you just created and will dump out a pretty sizable C file. You can skim through it and see what makes sense, compile it and run it. And then another important command is WASM interp. So that's the WASM interpreter that I was talking about a minute ago. You can take your example.wasm file that we just created and run it. Because this is a module that just exports one helper function, there's not going to be anything useful or exciting that comes from running this module. But it's important to understand that the tool is there and how you would use it. And then next, I wanted to show an example of WASM object dump. So this is nice because you can actually disassemble your WASM file and see, what the code is that was generated. So this is the command that I ran. I passed the -- disassemble flag, and then the example.wasm file that was just created. And you see example.wasm file format is wasm0x1. So that's a hexadecimal representation of the number 1. So this is basically WebAssembly version 1. And then the code disassembly actually shows what your WUT input was compiled down to. And you can see we have a get local 0, a get local 1, an i32.add, and then end. And that corresponds to our two get locals and our i32.add from our input function. So that's just a nice way to be able to compile a WASM file and see exactly what is inside of it. This is even less human friendly than what. So you're probably going to use this only for debugging purposes, but still, it's good to know that it exists. So now that we have a good understanding of what WebAssembly is, I wanted to explain how you would use it from your JavaScript code. So this is an example in Node.js. There are also, most of these APIs exist inside of the browser as well, but I'm going to focus on Node here. So we're at the very top, we're requiring the FS module so that we have a way to read in our example.wasm file. You could also, there's a number of other ways that you could read this in. You could download it from the internet or something like that. You just have to get the bytes somehow. So then we have an async function wrapper. I've wrapped it in an async function because we're using await inside, and also because there's two separate examples, I wanted to kind of isolate them. So the first one is going to be basically explicitly compiling and then instantiating the WASM module. So we use the WebAssembly.compile and the WebAssembly.instantiate APIs. And then from there, we can actually call the instance.exports.add_to function. That is the function that we created back in our what example. And then you can actually skip over the WebAssembly.compile step and just do an implicit compilation with WebAssembly.instantiate, which is what's shown in the second example. If you were using the browser or something else that supports fetch, there's actually a WebAssembly.instantiate streaming where you can pass the result of a fetch into it, and it will, as the bytes come in, it will compile it in a streaming fashion. Inside of Node, there's actually we have something called experimental WASM modules. So it's behind a command line flag, so you have to pass that when you're starting Node, but you can actually import WASM files directly. So if you're using ESM, the syntax is shown at the top. You would just do import star as example from example.wasm, and then you can call the add_to function directly. If you're still using CommonJS, which ESM is the future, but a lot of code is still in CommonJS, this is what it would look like. So there is no import in CommonJS, but there is dynamic import. So that's what the await import is doing right there. And then once you have your WASM file loaded, it's the same usage as ESM. So now that we know how to use WebAssembly from JavaScript, we can get down to what this whole topic or this talk is about, which is the WebAssembly system interface. So this was originally announced back in March of 2019. It was inspired by two projects called Cloud ABI and libpreopen. So neither of those projects, from what I can tell, ended up being extremely popular, but they had a lot of really good ideas that the WebAssembly folks were able to repurpose for this thing called WASI. So as I mentioned earlier, WebAssembly is sandboxed, and there's not really any way to access the underlying system. Even if you pass in a JavaScript function from, if you're running in the browser, that doesn't necessarily have a great way to access the underlying system either. So WASI really kind of improved WASM's non-web use case by providing, and I call them system calls because they generally let you call out to the system, but they're really just functions that are passed in. And you're able to do a lot of low-level system things like real-time and monotonic clocks. You can provide environment variables and command line arguments to your WASI application. They don't necessarily have to be the same environment variables and command line flags that are passed into Node or whatever the host runtime is. You can customize that. And then there are a lot of file system operations that work on file descriptors and string paths. And so WASI actually has a really good security model. Like I said before, security and sandboxing is important to WebAssembly, so it's got to be important to WASI as well. When you start up a WASI application, you give it a sandbox to play in. And if it tries to escape from the sandbox, any API calls that try to do that will return this special error called WASI not capable. Similarly, all of the system calls have what are called writes associated with them. So I listed a couple here: WASI write path open. That's basically a write that your code has to have to be able to open a file, or the WASI write path remove directory. So if you try to remove a directory and you don't have permission to actually remove directories, then your call will fail with the WASI not capable error. Another thing that's part of the security model is that all of the system calls are based on sandboxed resources. So instead of calling a function like open, which you just pass a string in and the environment tries to open that file, you would do something like open at, where you pass in a file descriptor and the file name is kind of relative to that file descriptor. So I'll show an example of that in a minute. So the way that the sandbox is defined is with something called a pre-open. So when you're creating your WASI instance, you give it a list of paths that are going to basically be your sandbox paths, and you tell the system how those map to actual host paths. So every time that a system call happens and WASI tries to do something, it'll resolve your path that you give it to something in the sandbox. So if it's not a valid path in the sandbox, then the operation will fail. If it is, then it'll take that sandbox path and translate it into an actual host path. And then an important note here is that each pre-open that you give it is given its own file descriptor. And I'll show you on the next slide how that is important. But down at the bottom, I've shown just an example of what a pre-open setup might look like. So on the left-hand side, we have the host path, which is everything is going to be living in your temp directory, but you can sandbox that to whatever you like. So for example, if your WASI application tries to access the etc password file, what will really happen is you'll be pointing at /temp/etc/password on the host machine, which may or may not even exist. And so whenever you go to access a resource, this is what the function signature for creating a directory looks like. All of the WASI calls will return this WASI error node type. That just describes if there was an error or not. So if it succeeds, there's a success error. Otherwise, the appropriate error is returned from the system. And when you want to create a directory, you have to give it the name of the directory. That's what the path argument is. WASI also, whenever you pass it a string, it expects the length to go along with that string. So that's what the path length is. So that's how you would create a directory. But the interesting thing here is that you're also passing in a file descriptor. So this would be, for example, one of your pre-opens. And so you'll say, I want to create the path or the directory /foo, but it's going to be relative to one of my pre-opens. So if it's not actually relative to one of those, then it'll fail with the not capable error. So WASI supports two different types of modules. The first one that a lot of people will use at first is called commands. These are analogous to applications in WASI. So they have a start method, _start. It takes no arguments and doesn't return anything. You can think of it as your main function. So it's called at most once, and this is kind of the way you pass it in. It runs it, and then once everything finishes inside of your start, you call WASI proc exit, and it completely exits the process. The second type is called a WASI reactor. So these are basically all modules that aren't commands. You can think of these as kind of utility modules. So you might have, if Lodash were a WebAssembly module, it would be a reactor because you're passing in all these like helpful functions. Reactors can have an _initialize method. That's if you need to do any setup. It's expected to run at most once, but it doesn't even have to exist. Next, I wanted to talk briefly about how you would compile from C to WebAssembly. So in a C application, there's something called libc. WASI has something similar with the WASI libc. You can use it with Clang. You would have to compile it locally and then compile your C file down to a WASM file. It takes a little bit of manual setup, but it's really not very, very tricky. So that's kind of WASI in a nutshell. For me, whenever I first heard about WASI in March of 2019, I was like, thinking about JavaScript. It's an open web technology. It's sandboxed. It's largely associated with the browser and can't access the system. I was like, that actually sounds a lot like WebAssembly. And then thinking about Node and libuv, they provide kind of the access to the underlying system. So I was like, this WASI thing, it sounds like libuv, but for WebAssembly. So I created something called UV-WASI, which is a C library built on top of libuv. It implements the WASI system call interface. It's designed to be part of a larger project, not run on its own. I've created I've included the link here at the bottom of the slide. And then we took UV-WASI and we embedded it into Node.js. So we created C++ bindings for it and a small JavaScript API. We didn't want to commit to a large JavaScript API because it's still very experimental. But so now there's a WASI core module starting in Node 13.3. It's been backported to v12, but if you want the best results, you should use v14.x. And then there are 2 command line flags that are required. So experimental WASI unstable preview 1 enables WASI support. Unstable preview 1 is the actual version of WASI that we're running, because WASI itself is still pretty experimental. And then if you're doing anything with 64-bit values, you're going to need to also pass the experimental WASM big int flag. So this is just kind of a code sample of what WASI looks like inside of Node. So the key things here are we're requiring the WASI module and getting the WASI constructor. We're passing in args, environment, and pre-opens to
5 minutes left.
Okay. To kind of define what our sandbox will look like and what the system can see. And then we're creating this thing called an import object. So again, WASM modules require imports to interface with the outside world. So we're passing in our import object that we've created, and then we're just running our WebAssembly code with wasi.start. So one of the things we ran into while embedding into Node was interfacing with the WASM memory. So WASI and WASM are always little endian, but the host machine may not be. So I've kind of showed the difference in how a little endian value versus a big endian value are represented in memory. The bytes are in a completely different order. So if you don't take that into consideration, your program will definitely not run correctly because it'll be reading all of the wrong values. WASM also has its application binary interface that it requires you to adhere to. So sometimes when you're writing these things to memory, you have to pad your structures. Sometimes, depending on the host that you're running on, your pointer values might be 64-bit, where WASM is always 32-bit. So we built into UV-WASI serialization and deserialization utility functions that take all of these things into account for the embedder. So it reduces the amount of boilerplate the embedder has to deal with. And also, these are implementation details for the embedders, so there's no need for them to have to keep writing it over and over. We also built in a way to trace WASI execution. So in Node, you can pass the node debug native equals WASI CLI option. If you're building UV-WASI from source, you can pass in the UV-WASI debug log option. Inside of Node, this is what a trace will look like. So it basically shows a number of WASI calls. The first 5 calls are how WASI kind of discovers its pre-opens. It just keeps probing, file descriptor 3, 4, 5. Since file descriptors 0, 1, and 2 are reserved for standard input, output, and error, you'll see that it gets to 5. It gets an error back there, so it doesn't call fd prestat dir name again. The environment calls are kind of, just loading up environment variables, and then it does some file open and some file write, and then a file close. This is the same code traced in UV-WASI. It's more detailed. It shows native things instead of sandbox values. I'm not going to run through this right now because I'm running a bit low on time. You can also run
10 minutes left.
You can also run multiple WASI commands inside of Node. So the trick here was that WASI commands exit the process. So we introduced a flag called return on exit, where you can run a command, and then instead of hard exiting your process, which would kill the node process, it'll actually just return the exit code, and then that way you can run multiple things, in sequence or even in parallel. So currently, you can't run WASM as the main entry point, and there's not really CLI flags to deal with these things. So you have to write a bunch of boilerplate over and over. So I created an NPM module called WASI Worker. It sits on top of Node's Worker API. I encourage you to play around with it. You really just need to learn one function signature, and then from there, it's the same as working with Node's familiar worker threads. This is a short example of what it looks like. Again, you're creating a WASI worker and assigning it to this worker value, and then interacting with it via Node's familiar worker threads API. And then briefly, I wanted to just cover UV-WASI has been
1 minute left.
Has been embedded into the WASM 3 WebAssembly engine. So that's nice because it lets us run on platforms that Node doesn't typically run on, so we get better system coverage and test coverage. And now WASM 3 can actually host itself now that it has full WASI support. There's also initial work to integrate with Wabbit so that you can run the WASM interpreter and potentially one day WASM to C. Future work is, the WASI spec is still evolving, so we're going to continue to evolve with it. Bug fixes. Windows has some concepts that other platforms don't. Continue to fix bugs and potentially upstream things to libuv. Node.js doesn't currently support reactors, but if you have any questions, please contact me. All right, and that is everything. Thank you.
Thank you, Colin. That was just amazing. I really enjoyed that. We've got actually quite a lot of questions. People are getting interested, so I'm sure you'll get much more insights on the Q&A session. Thank you. How do you feel about this conference? So how it was?
Good. I think this is my first virtual conference ever, but it's nice. It's doesn't require traveling all over the place, jet lag.
Yeah, especially the jet lag. Thank you. That's really good. The good thing. Congratulations. That's the first, but I hope not the last, your virtual conference. And thank you. Join the Q&A session, and thanks for everything that you shared.
Yes, thanks again for having me.
Thank you. Goodbye, Colin.